So today we're going to be doing graphs with limited ranges. Likewise, we've seen in previous videos where we had limited domains. If we had a limited domain, that meant that we were covering the graph from a left and a right standpoint. Likewise, a graph with a limited range means we're limiting the y value. It's the same concept, but we're going to be given both a bottom and a top, or maybe just one or the other. So it might have a minimum value, but it can go up as high as it wants. Or it might have a maximum value, but it can go down as far as it wants. So let's take a look and see how that would actually apply. So the minimum point is what we call the floor, and the maximum point is called the ceiling. These limitations are almost always the result of some limitation, not the cause itself. Meaning if you see a graph go up, 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 and then it just stops, most of the time that's the equipment. We can't measure past a certain point, like Geiger counters. Historically, during like Chernobyl, we said, oh, hey, the maximum amount of radiation was right here. That was a ceiling, not of the actual amount of radiation being sent out, but due to the limitation of the technology. We couldn't measure beyond that point. Likewise, if we're measuring minimum distances, now we have a concept called absolute zero. The idea is that we have a floor to this function. We can't get past absolute zero. Not because it may or may not be physically possible, but due to the fact that we can't get anything there. We can't actually make anything absolute zero. So again, range limitations are mostly the cause of our equipment. So let's take a look at what we have here. Now our first equation, what we're going to do is we're going to graph these, and we're going to graph these in pencil very, very lightly. Because a lot of what we're about to do today is we're going to be erasing. Now I have this equation. I know this equation is in y equals mx plus b format. So I need to find where do I start and what is my rate of change. Well, my starting point is going to be my b, which is the number on the end. That's a 2. So I'm going to start, let's say I'm going to make my graph today by 2's. And all graphs today are going to be by 2's. Some you can do, some you don't need to, but because I have this big old slope, I'm going to put all my graphs by 2's. So if I have a slope of 2, means I have a point right there. That is my start. And how I move is going to be my slope, which in this case is a -6. Anytime I have a -6, that's going to be over 1. So I know I'm going to be going down and to the right. So if I go down 6 over 1, well, I could go down 6 over 1 blocks and get that point. Or I could actually count and say go down 1, 2, 3, 4, 5, 6, and over 1. And what we notice is those are both in the same area. Now, if I can't go down and to the right, I'm just going to go the opposite and say, let's go up and left. I don't have enough room to go up 6 blocks, so how about just 6 units? So 1, 2, 3, 4, 5, 6, left 1. And so I have my points right there. And like I said, we're going to draw this in pencil because you're most likely going to be erasing most of what you see here. And so I have my graph, which looks something like this, in between these points. Now the second part of what we're doing today is we're going to be looking at this part, the limitation. So I have y is less than 4. Now, also, one of the other things that we do remember is we remember that less than or greater than is going to be an open circle. Less than or equal to or greater than or equal to is going to be a closed circle. Because of the bar beneath, I know I'm going to include the point. With no bar beneath, I'm going to leave an open circle. So I'm going to have an imaginary barrier at 4. So 2, 4. So I'm going to have some sort of barrier going on right here. And I know that y must be less than 4, which means I'm going to be going down. Anything that is less than 4. And at the barrier itself, I'm going to have an open point. So I'm going to draw an open point at the barrier, and I'm going to shade in everything on my graph that is below that value right there. Which means that, is there anything above the value? No, there's not, so we can go ahead and we can erase what's up here. I'm not going to fully erase. The idea is that the only part of the graph that we're going to be including is going to be the orange darkened area of the graph right there. So let's go ahead and let's try one more. I'm dealing with the equation of my line, anything before the semicolon right here. Again, I know this is y equals mx plus b format, so I need two things. I need my starting point, my b, which is -1, and how I move is going to be my slope, which is 2/3. I know 2/3 is rise, which is going to go up 2, over the run, which means right 3. And again, today I'm doing all my graphs. Each box is worth 2. So if I start at -1, I'm not quite down a box. Right here. Go up 2 boxes and over 3 boxes. So 1, 2, over 1, 2, 3. Again, if I didn't have enough room to do that, I could just go actually up 2 and 3 by counting. So up 1, 2, over 1, 2, 3. And what I notice is that it forms a straight line. So you can either actually count or do by boxes. It doesn't really matter. Up 2, over 3. And if I don't have room to go up and over, what I could do is I could go down and back. So down 2 boxes, over 3. Don't have enough room, so I might actually go down 1, 2, over 1, 2, 3. Down 2, 1, 2, over 1, 2, 3. So I have all those points in that line right there. And so I'm going to go ahead and I'm going to shade this in, but I'm going to shade it in very lightly because we're going to erase a good bit of this. This time, I'm looking at, I'm doing it in green this time because it looks like the orange was a little light. I want a barrier at y is greater than -4. So I'm going to come find -4 and I'm going to draw my little barrier. And I know y must be greater than or equal to -4. Which means first off, where my line crosses my barrier is right there. I'm going to shade that in because I'm including the -4. And I know I'm looking at anything that is greater than -4. So anything that is above it, these are all greater numbers. Perfect. I'm not actually going to include anything down here. So you can actually, if you want to, just go ahead and erase it. Perfect. There you go. So what I want you to try is I want you to pause the video real quick, and I want you to try out graphing this one. Now this one has 2 barriers, so it's going to have a floor and a ceiling, but at least start out with this, graph the line, and see how well you did. If you need help on this, just go ahead and watch the video through, but give it a shot, give it a try, and resume the video when you're done. Okay. So let's see. I have this is y equals mx plus b. I know that my starting point is going to be, looks like a -1, so my b is -1. And I know how I move is going to be my slope. I don't actually see a number in front of there, so I'm going to assume that there's a 1, which means 1 over 1. So it's going to go up and right. So I think that's enough to graph. Actually, I need to put 2's on both my x and my y. So I'm going to start at -1, which means I'm half a block down, -1. And I'm going to go up 1 block, right 1 block. So up 1, right 1. 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 And again, I didn't need to go up block over block. What I could do is actually go up 1 over 1. But what I'll notice is that my up 1 over 1 is always in between my blocks. So I'm going to end up creating a straight line no matter how I do it. And if I can't go up and right, I'll just flip it and go down and left. So down 1 over 1. Down 1 over 1. Down 1 over 1. Down 1 over 1. Perfect. So that's going to give me a line that's going to go through all of these points. Just like that. But in this case, I have the 2 barriers. Now, what I'm going to notice is that I'm going to end up splitting these into two different versions. So let's go ahead and let's start with the orange one. So I have y is greater than -2. So I'm going to come find -2. I'm going to draw a little, and you don't actually need to draw the barrier. I add a little bit of this just to see where the intersection is. So I know that y is greater than, because it opens towards the y, so I'm going to keep it opening towards the y. Y is greater than -2. So I know at the point, I'm going to have an open circle, and I know I'm going to shade upwards. But pause, because I actually don't know how far up. Am I going to go all the way up to the end, or am I going to stop somewhere? So that comes with my next part of my graph. I have y is less than 5. I'm going to draw a little make-believe barrier at 5. So now y, because it's opening away from the y, I have 2. I'm going to read this in two separate versions. Y is less than 5, or y is greater than -2. The y is in both inequalities. But regardless, I know that at the point where it intersects the 5, it's open. And less than means it's anything down here. And so what I have is I have this hybrid graph right here. Anything above -2, but below 5. I'm not actually including both points. And anything below -2, don't care about, so I'm going to go ahead and I'm going to erase. Anything above 5, I don't care about. I'm going to go ahead and I'm going to erase. And there we go. There's our graph. So that may have worked out pretty well with slope-intercept form, but how might you graph it in standard form? Now, standard form, we basically just graph it. We could either convert it into slope-intercept form, or what we could do is we could graph using the x-intercept and the y-intercept. We know for the x-intercept, I plug in y is equal to 0, and for the y-intercept, I plug in x equals 0. To find where it crosses the ground, I have a 0 height. To find where it crosses the wall, I have 0 depth. So I say, okay, let's plug in y of 0 into that equation. So x plus, plug in my 0. X plus 0, well, that's going to cancel itself out. X equals -3. Perfect. And so for this one, x is 0 to find my y-intercept. So plus y is -3. What plus y? Well, 0 plus y. 0 just basically cancels itself out, so I have y equals -3. Perfect. So as we said, that today we're doing everything by 2s. If I have a point at -3, so 1, 2, 3, and y at -3, so 1, 2, 3. I have those values. And so if we graph our line right here, just like that, we have this. And we know that we're dealing with a y is greater than -2. So I'm going to draw my little imaginary barrier, -2, and say y is greater than -2. I know because there's no equal sign, I know at the point where they cross, it's an open circle, and I'm dealing with greater numbers. So I'm shading anything that is above that point right there. Perfect. Everything below, we can just go ahead and get rid of. It doesn't need to exist. There we go. So having seen that, you might want to give number 9 a try. If not, we're going to go ahead and you can try number 11 here in just a moment. But why don't you give 9 a shot and see how well you did. Okay. So I'm dealing with standard form, which means I need to find my x-intercept by plugging in a 0 height. I need to find my y-intercept by plugging in a 0 width. Perfect. So 0 height is going to be x plus 2. And for this, it's going to be plus 2y equals 4. So, I'm plugging in a 0 height, and down here I'm plugging in a 0 width. Well, for the 0 height, that's going to cancel out, so I'm left with x equals 4. For my 0 width, that's going to cancel out, so I have 2y equals 4, which means I need to divide both sides by 2, which is going to leave me with a y equals 2. So, if again, us doing our value by 2's, I have an x of 2, 4, and a y of 2. Connect those with a line. Or if I don't really want to connect them with a line, I can say, okay, that's up 1, left 2, up 1, left 2, up 1, left 2. Or down 1, right 2, down 1, right 2. I can add a few extra points just to make sure I'm graphing this correctly, but boom, it looks like a straight line to me. So I know that I have y is less than or equal to negative 2. So I'm going to come find my negative 2 and draw a little imaginary barrier and say y must be less than or equal to negative 2. I know at the point where they cross, it must be shaded in because I have or equal to. And I'm looking at anything less than, which means anything below the line right there. Which means a good portion of this line, everything above it can go ahead and be erased. So most of my line is just going to end up going away. I'm only dealt with this last little piece right here. Okay. And so what I want you to try is I want you to try this last one where I have this equation and I have that barrier. At the bare minimum, try and go ahead and graph the line and see if you can't figure out what's going on with these two barriers, or just go ahead and try the whole thing. Resume the video when you're done, and if you had any questions, see how well you did. Okay, let's take a look. I want to find my x-intercept by plugging in a 0 height, and my y-intercept by plugging in a 0 width. So 0 height means 2x minus 3 times 0. And for 0 width, it's 2 times 0 minus 3y equals 6. And I'm going to plug in 0 for the y and for the x. That's going to cancel itself out, so 2x equals 6 divided by 2. So that means x equals 3. Over here, kind of the same thing happens. We have a negative 3y equals 6. We divide by negative 3, which means y is equal to negative 2. Nope. Doing these all by 2's. So we have an x of 3, so 1, 2, 3. And a y of negative 2, 1, 2. So in essence, what I'm seeing here is up 1 over 1.5. Up 1 over 1.5. Up 1 over 1.5. Or down 1 left a half, 1.5. Down 1 left, 1.5. Down 1 left, 1.5. Really, I'm just dealing with those two, so connecting those 2 points should connect all points along my line. And lo and behold, yes, it does. But in this case, I have 2 barriers. I have y opening towards y, so y is greater than or equal to negative 4. I'm going to say, okay, cool. Draw my little barrier, negative 4, and say it's greater than or equal to, which means equal to I shade in the point, greater than I shade up. But how far up? Well, look at my next one. Y is less than or equal to 0, so I draw another little borderline. I say y must be less than this. So again, I'm going to shade in that point because it's less than or equal to. I'm going to shade down. How far down? Well, that's dictated by the other equation. So boom, there we have it. Starts here, ends here. Everything else you can go ahead and erase. And there we go. So today we're going to be graphing piecewise graphs. This is basically a version of like Frankenstein graphs. We're graphing regular lines like we've been doing, but the big thing that we're going to be doing now is we're going to be graphing
part of a graph and part of a graph and smashing them together. So let's take a look at what that would entail. So I have a left and right of 0, which means that I'm going to have something that happens at the point of 0. So I'm going to go ahead and I'm going to draw, a little difficult to see because my axis is so dark, but I'm going to draw a dotted line right at 0. This means there's an event at 0. Something happened where my graph is split. On the left part of the graph, I have this. And I recognize that this is going to be a horizontal line because if I put it and compare it to my formula of y equals mx plus b, I'm going to say, okay, I know that my line, my y is still on the left, and my 3 is still on the right. And I'm going to line them up and say, okay, what values do I see here? Well, I know I'm missing an mx, which means that the only way that I could get rid of the mx would be if my m was equal to 0. And here my b, or my y-intercept, is going to be equal to 3. So if I count up 1, 2, 3, and put an intercept, and did a flat line, I would have this whole graph right here. Now, this would be if the graph went on forever. Unfortunately, I'm only looking at the left part of the graph, the left of 0 for this. So I'm only looking at this side. I'm actually going to go back and erase anything that was on the right of my event line. And I'm going to shade it in. So I have my graph over there. What happens at the event, it's a little unclear on this. We're going to go ahead and we're going to assume that it's going to be a circle, an unincluded point, which means that I'm dealing with, to the left of my event, any x values that are less than 0. So if I wanted to put a domain restriction, that would be how I would write left of 0, is x is less than 0. I'm going to do the same thing on the right part of my graph. I'm going to compare my line to y equals mx plus b. And I'm going to write the equation. Well, y is on the left, good. And -1 is on the right. This also doesn't have an m, which means the m must be 0, so it's a flat line. And my b is -1. This is where I start. So I'm going to come down here, I'm going to say, okay, at -1, let me draw a flat line. So I have a nice little flat line right there. But I'm not looking at the entire line, both on the left and right side. I'm only looking at the right of 0, which means I'm only looking at the side of my line that's on the right of my event. Go ahead and erase whatever's on the left of the event, because that is unimportant to us. And I'm going to shade in this right here, show that it goes on forever, and put an open circle at the event, because we don't know whether or not that's included. But anything to the right of the event, well, I'm looking at x values in relation to 0, x values that are greater than 0. So that would be the domain restriction that I would put on this graph if I wrote it as an inequality instead of as a description. So that's the basic idea of lines. Let's try something that instead of flat lines are diagonal lines. And the process is the same. We're going to find where our event happens. In this case, it happens at 0 again. So I'm going to draw my event line, my event at 0. And I'm going to say, hey, I'm going to compare this to y equals mx plus b on the left line, and I'm going to compare this to y equals mx plus b on the right line. Well, my left line is going to be y is equal to 2x. Doesn't look like there's a b. So if I line this up and say, hey, the number that's in where the m is must be my slope. So 2. So 2 over 1. And because my b is non-existent, it must be a b of 0. So I'm going to put a point at 0, and I'm going to go up 2 over 1. Up 2 over 1. And if I don't have room to go up and right, I'm going to go down and left. Down and left. And I'm going to connect these points with a straight line. Do it this way. I'm going to connect them just like that right there. But the big thing is this line goes on forever. I'm not concerned with the entire line. only the left part of the line. So I'm going to go to my event and only include the part to the left. I'm actually just going to go ahead and erase what I have on the right, which means that I'm only looking at this part that goes down here. I'm going to draw an open circle right there, which means concerning my 0, I'm looking at values that are less than 0. Less than is on the left. For my other line, I'm going to set it up the same way. Y is equal to negative 2x. Again, no b. So I'm going to compare these and say, hey, I figured out that my m is negative 2. Any number is going to be put over a 1. And because I don't have a b, my b is 0. So I'm going to come here and I'm going to say, okay, b of 0. I'm going to find my slope is down 2 over 1, down 2 over 1. If I don't have room to move down and right, I'll move up and left, up and left. And I'm going to connect these points with a line. So I have that. But again, that would be the entire graph. I'm not looking at the entire graph. I'm only looking at the right portion of the graph. So anything that's going on the left over here, I'm going to go ahead and I'm going to erase. Let me go ahead and darken what we have over here. Boom. I'm going to draw an open circle. So these actually connect at that point. But I'm dealing with x values that are greater than my event. So again, if I wrote this as an inequality, that would be what this would look like. So what I want you to try is I want you to try number 5 real quick, knowing that our event is right here in the middle, just like the previous two, and unpause the video when you're done to see how well you did. Okay, so let's take a look. So my left of 0, because these are lines, I'm going to compare this to y equals mx plus b, which means that I have y is equal to x plus 1. I know that the number in front of x should be my slope, but I don't see a number, so I'm going to assume that it's the number 1. And because it's a whole number, I'm going to put 1 over 1. My intercept is also going to be 1. Lots of 1s going on right here. I know that I have my intercept at 1, and I go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. If I don't have room to move up and right, I'll move down and left, down and left, down and left, down and left, down and left. And I'm going to connect all these points right here with a line. But I know that that's the infinite line. I'm only looking at the left portion of the line. So I'm going to go ahead and say, hey, anything on the right, get rid of it. And I'm going to say, hey, only the left values make it. In fact, x is less than 0 is how we classify left. I'm going to compare this y equals mx plus b to my right side equation, which is going to be, in this case, y is equal to negative x plus 1. I'm going to look at the number that's in front of the x, knowing that that is my slope. I don't see a number, but I see a negative sign. So when I don't see a number, it's going to be a 1. But because I see the negative sign, it's going to be a negative 1. Because that's a whole number, I'm going to put that over a 1. And then my b over here is also a 1. So I'm going to start at 1. I'm going to go down 1 over 1. So down and right, down and right, down and right, down and right. If I don't have moved down and right, I'm going to move up and left, up and left, up and left, up and left. I'm going to connect all these points with a straight line. Just like that. Now, again, this would be the infinite line. I'm only concerned with the part of the line that's to the right of 0. So I'm going to erase the left part and darken in the part that's remaining. Shoop, shoop. There we go. And again, I'm looking at values that are greater than 0. That's all that we care about. Awesome. Let's try a few more. So what we've got going on here is that our events are no longer at the origin. This time, my event is at positive 2. So I'm going to draw a line right here. My event is at, I wrote 0. We've had so many of those, I just wrote it again. So my event is at positive 2. So I'm dealing with x values that are to the right and to the left of positive 2. We're going to do the exact same setup though. My left equation, I'm going to say, let's take a look at y equals mx plus b. Let's compare the equation that I have right here. Y is equal to 1/2 x. I'm going to look at the number in front of x and say that must be my m. So my m is 1/2. And I'm going to look at the number that doesn't have an x, which isn't there. So that must be a 0. So I'm going to take my equation, put a point at 0, and move up 1 over 2, up 1 over 2. If I don't have room to move up and right, I'm going to move down and left, down and left. This is going to allow me to graph that line. Now, I'm still dealing with the left portion of the line, but I'm not going to race to the left of 0 or to the right of 0. I'm going to race to the right of my line. It allows a little more of my line to kind of work its way over. So I go all the way to there. And I darken this and say, boom. I'm only dealing with x values that are less than 2 because my event is now at 2. And I set up the same process for my right side equation. Y equals mx plus b. We're going to take the equation of the line. Y is equal to negative 1/2 x. And I'm going to look for the number in front of the x. And I know that that is my slope, negative 1/2. My b, which is my number out here, which doesn't exist, must be a 0. Kind of looks like a d, but we know that that's a 0. So I'm going to put my point at 0, and I'm going to go down 1 over 2, down 1 over 2. And if I can't move down and right, I'm going to move up and left, up and left. Perfect. And so let's connect all these points. So I have that. But again, I'm only dealing with the right portion of the line. So anything that's to the left of the event, we're going to go ahead and we're going to erase. Get rid of all that. Draw my circle right here, and I'm going to darken the right side of the line. In this case, I'm only dealing with x values that are greater than 2. Awesome. So we see the setup is exactly the same no matter where that event takes place. If we look at number 9, the same thing is going on. This time the event is going to take place at positive 1. So it's a little closer. The setup's exactly the same. You have a left side and a right side, both of which are compared to mx plus b because we have lines here. So now my left portion is going to be y is equal to 2x plus 1. The number in front of the x is going to be my m, so my slope is going to be 2. I turn that to 2 over 1, so I have a fraction. My b is out here. B this time is 1. Again, the same process that's compared to the right side. Y is equal to 2x minus 1. The number in front of the x is your slope or your m, so 2. If it's a whole number, put it over 1. Your b is the number on the outside, the number without an x, which is negative 1. So we see we've got our two equations set up pretty heartily there. For my left one, I know I'm going to start at 1, and I'm going to go up 2 over 1, up 2 over 1. If I don't have room to move up and right, I'm going to move down and left, down and left, down and left. Boom, I have that. I'm going to make it to the left of my event. How do we say that in math? Well, I say I'm dealing with the x values that are to the left of 1, or x is less than 1. Boom, just like that. On the flip side, if I'm looking at my blue equation, I'm going to have a b at -1. But I'm still going to move up 2 over 1, up 2 over 1, up 2 over 1. If I don't have room to move up and right, move down and left, down and left. Ooh. So what do we notice about these two lines? These lines move at the same rate and they have different y-intercepts. I believe that would be what we would call parallel lines. But unfortunately, we don't need the entire parallel aspect. I'm only concerned with the right portion. So what could have been parallel is no longer, because they're not actually running side by side. They're running on different portions of the graph. In fact, this one I'm only dealing with values that are greater than 1. My little event right here at 1. Perfect. So what I want you to do is I want you to pause the video, and I want you to try number 11, unpause the video when you're done to see how well you did. Okay. So this one is a little bit of a tricky one because I have two different types of lines. I have a flat line, or a horizontal line, I should say, and a diagonal line. So I know with the first one, when I plug in y equals mx plus b, and I write my equation, I'm not going to have the m. I'm just going to have y and a -1. There's no x, there's no number in front of x, which means my slope is 0. I know my b is -1. And I have an event at -2. So I have an event at -2. I'm going to have a point at -1 and a flat line. I know I'm only dealing with the left part, so I'm actually going to erase all of that. I'm just going to draw my hook and the fact that my line keeps going all the way over there. So any value less than -2. For my other line, I'm going to compare that to y equals mx plus b. And I have y is equal to x plus 2. Again, we've noticed that if there's no number in front of the x, it must be a 1. If it's a whole number, put it over 1. And my b is the number on the outside. So if I have a point at 2, I go up 1 over 1, up 1 over 1, up 1 over 1. If I don't have room to move up and right, I'll move down and left, down and left, down and left, down and left, down and left. I'm going to connect all these points right here, but only use the points on the right. I'm going to erase everything that's right there, which means draw my hook, and everything that's on the right, any value that is to the right of -2 or greater than -2. And there we go. So today what we're going to be looking at is relationships and functions. Now, the whole idea of any graph, any set of values, any coordinates, any mapping diagram, any table of values can be expressed as a relationship. If you have an input, you have an output, you compare up two numbers. Now, the difference between a relationship and a function means that if I ask you a question, you can only give me one answer. And the way we phrase that is for every input, there is exactly one output. For every x, there is exactly one y. So let's take a brief look at what it would mean if when we ask a question, we get two answers. If I have one input, one x, I have more than one output. And this is going to be what we call having an object in superposition. And so one of the common examples that people use is Schrodinger's cat. And at this level, Schrodinger's cat involves radioactive isotopes, it involves a timer, an alarm, poison, a cat in a box, and it can get a little confusing for somebody who's never experienced this. So let's start out with something I like to call Schrodinger's girlfriend. Let's assume there's this handy-dandy guy called Schrodinger, and he is feeling like he's hot stuff, and he found himself a girlfriend. And he's got a nice little girlfriend, and she's like, yay, they're in a relationship. There's a boy paired with a girl. Now, unbeknownst to Schrodinger, boy paired with girl is also paired up with another boy, and this boy's super cool. He has a hat. And so if we look at each aspect, each relationship, well, Schrodinger has his relationship with his girlfriend. And they are in love. They have a relationship. This is a relationship. Makes him happy, makes her happy. But unbeknownst to him, Schrodinger's girlfriend also has another relationship with this hot stud with a baseball cap. And they also have a relationship. We paired one girl with one boy. So we have boy paired with girl, boy paired with girl, girl paired with boy, girl paired with boy. We have an X and a Y. Now, the problem comes in is that these relationships are not what we call functioning relationships. Because once boy meets boy, they realize that girl has too many relationships. And so therefore, we say, hey, this function is no longer functioning. And we end the relationships. Now, this in and of itself implies that this is only a one-way street. In reality, this can apply in two directions. It doesn't necessarily just need to be the boy or the girl, because this says, hey, a boy can have a relationship with a girl, but a girl can't have a relationship with more than one boy. We'll get into that when we get through here, but I think this demonstrates the idea of what is a function and what is a relationship with pairing up relationships, and if one shows up more than once, it is not functioning. So non-functioning. So therefore, the relationship is broken. So let's see what that looks like in the actual language of math. So if we look at, let's start out with coordinates first. So with coordinates, what we're looking for is hey, do we see any girl, do we see any X value that repeats or is in more than one relationship? So we're going to scan through here and we're going to say, do I see 0 paired up with any other person? No. Don't see 5 paired up with any other person, or 8, or -7. But I do see over here that I have 2 paired up with 2, and in another area I have 2 paired up with 1. So just like our earlier example, albeit these are all relationships, girl is paired with 1, girl is paired with 2. So this is a non-functioning relationship, not a function. The way to tell that it is a function is that if we scan through every girl and say, hey, this girl has one boy, 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 this girl has one boy. Each X has exactly one Y and not more than one. So this checks out. This is a function because each X is in only one relationship. Down here, now I have an X paired up with a Y that's exactly like it. That's like saying, okay, we have a baseball player, and if we put the girl with a little baseball cap on and we said, hey, they're just like each other, it doesn't matter. If boy is paired with girl and girl is paired with boy, we don't care what they look like. We're just trying to find, do we see an X value in some other relationship? So let's say she pops up over here. Well, now she's just like him, but she pops up somewhere else. So I'm looking to see, do I see a 3 in any other relationship? No. A 5? No. A 2, 4, 1, 0. All of these are only in one relationship, so this is a function. And a number 15, what we're looking through is we're looking through the same thing. Most of these numbers are in only one relationship, but if I look at the number 0, I see that 0 is in a relationship with 2. This X has a Y, but this X also has another Y over here. This 0 is in more than one relationship. So we know that because of that, this is not a function. And so that's how to tell if a relationship is a function given coordinates. Well, another way we might show a given relationship is through a mapping diagram. And the way that we show a mapping diagram is we take each one of these coordinates. Let's say from least to greatest, I have a 0 as an x, I have a 1, a 2, a 4, and a 5. I put them in here, and this is my set of x's. Then I list all my y's, and I say, well, I only have a 1 and a 2 for my y's. And I just start pairing them up. I say, well, 0 was paired with 2, 5 was paired with 2, 2 was paired with 2, 4 was paired with 1. Do this with red on the right side. So 4 was paired with 1, 1 was paired with 1, and 0 was paired with 1. And what you're looking for is you're looking for any x. We noticed this x in this function repeated. So I see the fact this x is paired up with a 1 and a 2. So we're going to identify, do any of these x values over here have more than one relationship? And you just trace the lines. Okay, this x has more than one y. I have a line coming out and a line coming out. So I know this is not a function. If I go down a little bit, each x on this one has exactly one line coming out of it, which means that this function has exactly one y, or this x has exactly one y, this x has exactly one y, so does this one, and so does this one. So we know that each one of these numbers has exactly one y. Now, they all have the same y, which is where our earlier analogy with Schrodinger's girlfriend kind of starts to fall apart because it implies a one-way relationship. What this is saying is that we have 4 different x's, so girl 1, girl 2, girl 3, girl 4, who are all dating the same boy, and that is okay here. So we know that we need to come up with a better analogy, but again, this was just an introduction. So if all these girls are dating the same boy, we're going to call that a function, but if we have all these boys dating the girl, that's not functioning. So again, that's where Schrodinger's cat comes in. I suggest that you go read up what Schrodinger's cat, how that thought experiment works. So let's continue on. Now the flip side is, okay, this x has many different y's, and we can tell because it has many different lines coming out of it. I have 4 lines coming out of it. So what's going on right here is that this girl is in not 1, not 2, but 4 different relationships. There are 4 boys that she's in a relationship with. So we say this is not a function. And the last one right here, we notice that each x has exactly one y attached to it. So we're happy with this. This is a function. And then the next extension, from a mapping diagram, we went from coordinates to a mapping diagram to a graph. Now, a graph is one of the easiest ones to do because you can do what we call the vertical line test. You can test, we know that x is on the horizontal axis, and we know that y is on the vertical axis. We can test if each x has one y simply by drawing lines down the graph and asking how many times does it touch. And if it touches 1 or less, we're happy. So if I draw a line right there and I say, how many times does it touch my graph? I'm going to darken up my graph just a little bit. So that way we know what we're trying to touch. Touches my graph no times. So far, there's just no relationship over here. So function or not a function, there's no relationship. If I move closer, move closer, move closer. Well, if I move right here, it touches once, which means that this x value has one y. And same thing if I do it over here. This x value has exactly one y. They both only touch my graph once. But if I draw a line right down the middle right here, I know I touch my graph up here and up here. So that says at this point in time, I have 2 locations, or this particular girlfriend has 1, 2 boyfriends. So this is not a function. Same thing with the one below it. I can draw lots of lines over here where it implies this is good, 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 this is good. None of those are important because if I can draw a line anywhere, namely, let's say right here, this is saying each one of these lines is a girlfriend. They have exactly no boyfriends. It's not a relationship, so it's not functioning or not functioning. But over here, this girlfriend, this one line, has 1, 2 boyfriends. So this is also not a function. And now, unlike those, this one, you can draw as many lines as you want. Each line that you draw is a girlfriend. It touches your line exactly 1 time. So each girlfriend has exactly 1 boyfriend, no matter where you draw the line. It only touches the line, it only touches our graph once, which means each girl has 1 boy. Same thing down here. If I take my graph and I darken it so we can see this a little better, and I draw, well, all these girls over here have no boyfriends, so it's not functioning nor not functioning. We just can't say anything. But the girls right here, that girl touches our line once, which means that girl has 1 boy. This is a function. So both of these are functions. Okay. And lastly, how do we tell with the equation? Well, the equation is quite simple. We just look at, is the power on y more than 1? So here we ask, does a vertical line touch more than once? Here we ask, does the x show up in more than one relationship? Does the line touch more than once? Is there more than one line? From any x value? So is there more than one line coming out of any x? Does the line touch more than once? Does the x repeat? Here we're asking, is the power on y more than 1? So the first one, my y is right there. That's y to the first power. This is a function. Same thing right here. That 5 is the coefficient. I'm concerned with the power. So 5y to the power of 1. This is the important thing. I don't care that there's a 5 in front. I know that the power on y is a 1. So this is a function. Unlike this right here. This y is squared, which means that this graph is going to be a horizontal quadratic if you wanted to draw it. So I know that this doesn't pass the vertical line test, nor would it pass our equation test. So this is not a function. And the last one, if I see y more than once, I might be required to go ahead and simplify the equation. So I know y plus y is 2y, x plus x is 2x. Even though that turned from a 1 to a 2, the power of y, the number up here, the important part, is still the number 1. So now this is a function. There you go.